last thing we wanted to talk about was the frequency with which collisions happen in gases. So this is going to be important for a bunch of reasons. So, molecules, as they bounce around, are going to collide with one another, basically if they get close enough to touch. And by touch, I mean a molecule will collide if they approach within what's called the collision diameter. And so the collision diameter is the sum of the radii of the two molecules that are undergoing a collision, as long as we think of them as little spheres again. So we're going to continue to think of particles as these little spheres. So if we focus on this particular molecule, which we'll represent as a little sphere, as it flies through space at some speed, vx, it's going to basically map out a cylinder as it flies through space. And the cylinder is going to be of length, whatever its speed is, multiplied by a time interval that we happen to be interested in. And an area given by this, what's called the collision cross-section, sigma equals to pi times twice the collision diameter. So molecules will collide if their centers get within the collision diameter. And as long as we're talking about the same molecule, where the radius of molecule A and the radius of molecule B is the same, that's just the diameter of the molecule. Okay? So the molecule as it flies through space is going to sweep out this. It's going to sweep out this cylinder. So VREL is the relative speeds of molecules. If I multiply that by a time interval delta t, this is going to give me a distance. It's traveled in this interval. And again, that'll be in meters in SI units. On average, right? The speed is going to be a distribution. Molecules will all be traveling at different speeds. So, as this molecule flies through A, it flies through a certain distance, v times delta t. This molecule's center is more than a diameter away from the center of this molecule, so it will miss this one. This molecule's center is within this tube that's going to get mapped out, so it's going to collide with that one. Okay, so it will fly through space. It's going to collide with this particular molecule, and so the volume of the cylinder is swept out in delta t is going to be equal to, I'll call it the cylinder, the cross section times the relative speed times delta t. So how big are molecules in general? Well, the bigger the molecule is, the bigger the cylinder it will sweep out, the more likely it is to collide with another molecule that happens to be around. So the bigger the molecules are, the more likely they are to collide. The faster they're moving, the more frequently they'll collide as well, because the length of the cylinder in this time interval delta t will also be larger. So the area at the end of the cylinder is this collision cross-section, as I mentioned. It's pi times the diameter of the molecules. So you can get an idea. Since we've been speaking about N2, we'll focus on that one. We can calculate roughly what the diameter of an N2 molecule is. Again, we're approximating it by thinking about it as a little sphere. Not exactly a sphere, but it's round enough that that's a good enough approximation for us. The diameter of an N2 molecule, or any molecule, is going to be the square root of its collision cross-section divided by pi, which for N2 is going to turn out to be about 0.37 nanometers, or 3.7 angstroms if you prefer those sorts of units. So you can do similar calculations, and you can see that the collision cross-section for N2 is 0.43 nanometers squared, so that's 0.43 times 10 to the minus 18 square meters. A helium atom, well, it's about half the area, as you would expect. Helium is a much smaller atom than N2 is a molecule. CO2 is kind of similarly sized. A molecule like benzene, the six-membered ring, is bigger than an N2 molecule, again, as you might expect. And you can see that mapped out in terms of the size of these collision cross-sections. Yeah?
So that equation, diameter equals the square root of collision cross-section over pi. That's how you take the diameter of any molecule?
It's a way to estimate the size. You can measure collision cross-sections based on collision frequencies and so on, and you can determine a diameter in terms of turning that around. Again, this is an approximation. Remember, we're treating these molecules as being spherical. They're not. It's a rough idea. We'll do it roughly as treating the spheres. It's going to be close enough. But the cross-section is definitely a quantity that you can in principle measure and infer molecular size from that. Complicated because all of this assumes again that our molecules don't interact until they collide, but molecules do interact, as we'll come to when we speak about real gases in meters squared, I should say, is just 10 to the minus 18 meters squared. Okay, so how often do collisions happen? A molecule is flying through space, it's mapping out the cylinder. The number of collisions that happens depends on how many molecules there are likely to be within that volume that we map out as the molecule flies through space. And that depends, once again, on the number density of molecules that are present in our gas, the number of molecules per unit volume. And we've already seen what that is. It's the number of moles that are present divided by the volume of the system multiplied by Avogadro's number. That gives me a number density, specifically a number density that will be in units of molecules per meter cubed. Okay? So N is a quantity of molecules in moles. Avogadro's constant in units of inverse units of moles. The volume we will measure in not per meters cubed, meters cubed. And overall we get a number density in units of per meters cubed. So we'll call this quantity N the number density. So the collision frequency is the volume of the cylinder multiplied by the number density, the number of molecules per unit volume, divided by this time interval that we happen to be interested in, delta T. So everything cancels out there. And what we're left with then, if we calculate that property, is a collision frequency, which we can measure as the number of collisions per second. Okay. Again, the units should make this kind of clear. We've got a cross section here, which is going to be in square meters, a relative speed, which is in meters per second, and then a number density, which is in meters to the minus 3. Number of molecules per cubic meter. All of the meter terms, factors cancel out to leave us with a frequency of collisions per second. We can express the number density using the ideal gas law again. So I know that N over V is equal to P, the pressure, divided by the gas constant multiplied by the temperature. That's in molar units. That's my perfect gas law again. If I want to express this in molecular units, not the number of moles per unit volume, but the number of molecules per unit volume, I multiply both sides by Avogadro's number. That gives me the number density on the left-hand side, N, the number of moles times Avogadro's, divided by the volume, which equals the pressure divided by the Boltzmann constant times the temperature. And this is the number density in molecules then per cubic meter. It's worth having an idea what order of magnitude that number is. We know how fast molecules tend to be going, relative speeds of the order of a few hundred to 1,000 meters per second. We calculate that on Wednesday. Cross sections, you can see, are going to be of the order of 10 to the minus 18 square meters. They're usually about the order of a square nanometer, or just under. So to calculate the collision frequency, we also need an order of magnitude estimate for how many collisions a molecule will typically undergo. So let's do a quick calculation of that. Again, we're just going to use the ideal gas law to do this. So we'll calculate the number density at a pressure of 1 bar and a temperature of 298 Kelvin. This is called standard ambient temperature and pressure, which we'll abbreviate as SATP. Standard temperature and pressure is usually at the temperature of 273 Kelvin, and standard ambient is at 298. So my number density, N times NA over the volume, is equal to P divided by the Boltzmann constant times the temperature, as we've just seen. We can drop some numbers into this equation here, putting everything into SI units. 1 bar of pressure in SI units is 10 to the 5 pascals. So that's in the numerator. And then I'm going to divide that by the Boltzmann constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. And I'm going to multiply that by my temperature of 298 Kelvin. Units are there, pascals. Again, you can expand all these out into terms of basic SI units of kilograms, meters, and so on. All of the units are going to cancel out here and leave you with something that is in the units of inverse volume. If you plug these numbers into your calculator, what you're going to find is that this is about 2.46, I think, times 10 to the 25 N2, or any gas, air, even if you want, the number of molecules per cubic meter, and 1 bar of pressure, which is about ambient pressure, and the ambient temperature is about 10 to the 25, right? So there's a vast number of molecules per cubic centimeter, per cubic meter. And to highlight this a little bit more dramatically, if you think about a cubic centimeter of air, a very small volume, and we can divide this number by 1 million, we still have 2.46 times 10 to the 19 molecules per cubic centimeter of air. So every cubic centimeter of air contains about 10 to the 19 molecules, right? So it's a vast number of molecules that are present, and still most of that space, that volume is empty space, right? Because the molecules are a reasonable distance apart from one another. How far apart from one another are they? Well, that's the next part. What's the average distance that a molecule travels between a collision as it flies through a gas at this sort of pressure? Well, we can define a quantity called the mean free path, lambda. Okay? And lambda is given simply by the relative speeds of the molecules, which we can already calculate, divided by the collision frequency. Again, in terms of units, the relative speed is meters per second, and the collision frequency is seconds to the -1. And so that gives us a mean free path value, which we can again quantify in terms of meters. From the previous slide, we saw that the collision frequency was equal to the cross-section times the relative speed times the number density, where again this number density is P over the Boltzmann constant times the temperature, total number of molecules per cubic centimeter. And we can drop that into the equation and come up with this alternative formula for the mean free path. It's kT, the Boltzmann constant times the temperature, divided by the cross-section, divided by the pressure. It's probably useful at the moment to consider an N2 molecule and think about what the mean free path is, just to again get a handle on what the magnitudes of these calculations are. This says 1 atmosphere. I think I want it to be 1 bar. They're about the same number anyway. We'll round things, so it doesn't particularly matter. So N2, under these conditions, we can use some numbers that we've already calculated to make this calculation a little bit easier. So let's calculate Z first. We'll calculate both Z, the collision frequency, and then lambda, the mean free path. So let's deal with Z first of all. Well, Z is given by this equation here. We've already determined what each of these parameters are. Sigma, for N2, we've seen 0.43 times 10 to the -18 square meters. That was from the table that I reported on the previous slide. We calculated the other day what the relative speed of N2 molecules are. That was about 672 meters per second at 298 Kelvin. And we've just seen what the number density is under equivalent conditions. So the number density, P over kT, was equal to about 2.4 times 10 to the 25 molecules per cubic meter. So I can just take the product of these three numbers to calculate the collision frequency. And if I do that, I find that the frequency of collisions is 7.0 times 10 to the 9 per second. That is, their molecule of N2 bouncing around in the air undergoes something like 7 billion collisions every second. The time between collisions is just 1 over this number. So 1 over Z is then about 142 picoseconds. So every 140 picoseconds, my N2 molecule collides with another molecule, 1 atmosphere and 298 Kelvin. So how far does a molecule travel in that time period? Well, we can calculate that straightforwardly. We know the relative speed. We now know a collision frequency. We can just divide one by the other and calculate a distance. And so the mean free path turns out to be 672 meters per second divided by this 7 times 10 to the 9 collisions per second. And that gives me a mean free path of about 96 nanometers. A molecule of N2 at 1 atmosphere or 1 bar and 288 Kelvin undergoes undergoes a collision every 140 picoseconds, and it manages to travel about 100 nanometers before it encounters another molecule and undergoes a collision. On average, some collisions will happen with shorter time periods between them, but on average, that's the type of distance that they'll travel and the time between them. And the important point for our purposes, whether or not we think about things as perfect gases or not, is how does this mean free path, the distance traveled, compare to the size of a molecule? Well, we've seen the diameter of a molecule. The diameter of the molecule is about 0.37 nanometers. So the mean free path is actually several orders of magnitude larger than the size of the molecule, right? It's only about 0.4 nanometers in diameter, but it travels about 100 nanometers before it collides. So the molecules on average, relative to the size of the molecules, are actually very, very far apart from one another in a gas under these conditions. So lambda is very much greater than D. Again, our fundamental requirements for dealing with gases and treating them as perfectly is that they're very small, they tend to be, and that they don't really encounter each other very often. Well, on average, they're actually quite far apart from one another under these sort of conditions.
I have a quick question.
Yes?
Your answer for lambda, the 96 nanometers, did you already do a unit conversion without having written it down? So you divided 672 meters per second with 7 to the times 10 to the 9?
Yes.
How'd you get nanometers?
Because it would be 96 times 10 to the minus 7 meters.
Okay.
It's basically 7 times 10 to the 2 divided by 7 times 10 to the 9. 7 over 7 is 1. 10 to the 2 divided by 10 to the 9 is 10 to the minus 7.
I see.
So it's about 1 times 10 to the minus 7. Yeah.
Just for clarification, what units is that for the 2.4 times 10 to the 25?
Inverse meters cubed, meters to the minus 3. It's a inverse volume. Again, it's a density we're measuring, it's concentration, number of molecules per unit volume. Okay. You'll have to, if you run through the units and do calculations, you can write out what a unit of Pascal is, the SI unit of pressure. KT is basically energy, it's joules per Kelvin multiplied by Kelvin. So you can write out what units a joule is in SI units as well, and all of the masses and all of the distances will all cancel out in the appropriate way to give you meters to the minus 3 for them. But we're running through that just to make sure that you check that those units do cancel out in the right way. Any other questions about kinetic theory, or shall I talk about real gas?
I have a question about the,
Yeah.
on the, like, one of the previous slides,
Yep.
one of the units was, the sigma over nanometer squared.
What did I do?
It was just one of the charts, that chart right there. But weren't the units of sigma in meters squared? So, would they?
Yeah, those numbers are nanometers squared.
Oh.
So 1 nanometer is 10 to the minus 9 meters. So when you square it, that gives you 10 to the minus 18 square meters per square nanometer.
Yeah, but, I don't know, the notation, like, if you put the sigma into, like, the meter squared, or are you just saying that it's, sigma is in?
You can use it for whatever units you want. You just need to make sure that your units are consistent throughout. So the safest way to do that is probably always to convert everything into SI units before you plug them into the equations. If you're comfortable messing around with units, then by all means mess around with units. But the important thing is to do a sanity check at the end and make sure whatever value you get out is a physically reasonable number. Right? If you come up with a length of a molecule that's 0.37 meters, right, that's not reasonable. Molecules are tiny, right? It's not this big, right? So that's going to have to be the check. But plugging the units in the SI form is probably the right way. If you leave it as 0.43 over pi square rooted is 0.37, which is in nanometers already, because it was nanometers squared that went in. Or you convert it into meters squared and then get a number out of meters. Does that make sense?
Yeah, well, yeah, I was just confused, because I thought, like, you were keeping the sigma, but it's just a different notation. Sorry.
Keeping sigma where, sorry?
No, never mind,
We can talk about that.
Yeah.
All right. Okay, we need to talk a little bit about real gases as well. Although this is going to be important in some regards in terms of phase transition, but when things jump from being a gas to a liquid. But for the most part, if you're dealing entirely with gases, I've got to say, yes, I started my PhD back in 1997, and all of my research work has involved gases, and I've never worried about real gases. I've always treated gases as perfect, because it's a good enough approximation for most purposes, unless you're under extreme positions or you're an engineer caring about high pressure, high temperature sort of conditions. But under regular conditions and atmospheric sort of conditions, then the perfect gas law works well enough for the most part. So, when does perfect gas behavior or deviations from perfect gas behavior matter? Well, they matter, and what causes these deviations is probably the important thing to talk about first. But we have to worry about the intermolecular forces that exist between gas molecules. Okay, so the perfect gas picture, we can either ignore the concept of molecules altogether, or we treat them as hard spheres that only interact when they kind of bounce off one another. There's no attractive interactions between them otherwise. But for real molecules, there are attractive intermolecular interactions. It's an intermolecular potential between them that is controlled by a range of intermolecular forces. Dipole-dipole forces, dispersion forces, all of those sort of things that you've probably heard about in general chemistry. And again, it's because of these forces that molecules can actually coalesce and stick together and form condensed phases like liquids and solids. So, real gases are going to deviate when these forces start to become important. And the two main approximations that we've made, or we've assumed so far, is that there are no interactions between the molecules except these rare collisions. So we've assumed that molecules have negligible volume. And we've assumed that there are no attractive interactions. And neither of these things are true. And so the picture here is showing you an intermolecular potential energy curve. So this is how the energy changes as molecules approach one another. So if molecules are very far apart from one another, they have no way of knowing that they're there. But if you bring them closer together, as you move from the right in this diagram, then once they get to within a certain sort of distance, they start to feel the attractive interactions between one another. You bring them closer and closer, the potential energy falls because they're drawn together. Then eventually you put them so close together that they're basically in contact and their electron clouds start to interact and you start to generate repulsive forces between the two. At which point, if you keep trying to push them closer and closer together, the potential energy shoots up dramatically and the potential becomes repulsive. You can't push one molecule into the same space that's already being occupied by another molecule. So, what we have is, at very short range, we have repulsive forces that push molecules apart. And at intermediate range, there are attractive forces that help pull molecules together. Okay? And at very long range, the molecules are largely unaware of their existence. And this is why, at low pressure, you have basically perfect gas behavior for most gases. The molecules, on average, are so far apart, they don't know that one another are there. So again, the perfect gas laws, I just mentioned that the pressure times the volume is equal to a constant. So the limiting behavior is the perfect gas behavior. Which happens as the pressure goes towards zero, which is equivalent to saying as the volume goes towards infinity. So the lower the pressure is, the further apart the molecules are going to be on average. You can think about this in terms of the mean free path as well, and the volume of the system. The molecules have small volume, molecules physically. So the bigger the volume of the system, the smaller the fraction of the total volume is taken up by the physical volume of the gases. Most of the volume is empty space. Also, the mean free path depends inversely on the pressure, right? So again, the larger the volume is, the lower the pressure is, the larger the mean free path is going to be. Where in the limit that you go to zero pressure, which is where this limiting law holds exactly, then the mean free path goes to infinity. That is, on average, the molecules are so far apart from one another, they never actually interact. And that's when you get this ideal, perfect gas behavior. Just add that note. The mean free path is also going to go to infinity as the pressure goes towards zero. So real behavior is going to happen in this intermediate situation where the mean free path starts to become compatible or comparable to the size of the molecules. Once molecules get to within a few molecular diameters, well, we start being in this kind of region of the potential energy curve. That is, molecules tend to pull themselves together, right? Which means a gas is more easy to compress once you get to a higher pressure. You start compressing the gas from perfect behavior, the mean free path gets shorter and shorter and shorter as you decrease the volume and the pressure increases. Then you get to a region where the molecules are much closer together, and on average, they start to interact with one another, which pulls them closer together, because there's a force pulling them together, which makes compressing them a little bit easier. So once you get to these intermediate pressure regimes, where the mean free path is decreased to being comparable to molecular sizes, attractive forces assist compression, right? Then you push them closer and closer together so that your molecules are effectively in contact. And at that point, the repulsive interactions start to take over. The molecules start pushing themselves further apart. And as a result of that repulsion, the pressure goes up more quickly than you would expect. It's harder to compress the molecules further because they're already in contact. Yeah?
Your gas law breaks down at, it starts to break down when you like compress molecules into a tighter space, your gas into a tighter space.
At higher pressures, it will start to break down. Yeah. We can look at this on this picture here. It's a lot of pressure against molar volume this time. So let's talk about this in terms of a molar volume. I'll define the molar volume. Vn is the volume divided by the number of moles, which based on the ideal gas law is RT divided by the pressure. The molar volume is going to have units of meters cubed. Meters cubed per mole. So just to put this quantity in context, because this graph only goes up to a picture of a molar volume of 1 litre per mole. Let's consider a gas again at standard temperature and standard ambient temperature and pressure. So that's 1 bar, 298 Kelvin. Then the molar volume is going to be equal to the gas constant times the temperature, 298 Kelvin, again divided by pressure, 1 bar, or 10 to the 5 pascals. If we do that in molar units, that is 0.0248 meters cubed per mole of gas, or 24.8 liters per mole of gas. So that's like continuing all the way somewhere off the edge of the screen to see where our standard molar volume is. So if we're way off on this graph, all the way off to the right, we're at standard ambient temperature and pressure, and so a gas like N2, for example, behaves practically perfectly. Okay. The molecules are far enough apart. Yeah. Yeah, standard ambient temperature. So the only difference is the temperature part. Ambient temperature is considered 298 Kelvin. Standard temperature and pressure would be 273 Kelvin. So Vm at standard temperature and pressure is off on the right hand side. Yeah.
Could you reiterate why at around moderate pressure attractive forces are going to dominate?
Yeah, I'm going to talk about it in terms of this picture. Okay. So as you compress the system, again, you can think of your gas compressing in some kind of cylinder with a piston, so you can compress it, decrease the volume, right? As you compress the gas, the pressure goes up. Pressure times volume is going to be a constant. And in terms of the molar volume, then the pressure here is RT divided by Vm, right? And so the graph you plot there, plot pressure against volume, is you're plotting the isotherm. Okay, so this is an example of an isotherm calculated here for a temperature of 350 Kelvin. But the black curve is what you're going to expect to see if your gas behaves perfectly, right? So all the way out to the right hand side, you can see that and the red line represents behavior of a real gas. So you can see that there are deviations once you start to compress things down, once the molar volume gets sufficiently small, right? So off to the right hand side, at infinite molar volume, the pressure is going towards zero. That is, the molecules on average are so far apart from one another, they never encounter each other, and so the intermolecular forces between them are completely insignificant. All of our approximations and assumptions that we make in kinetic theory that they don't interact are perfectly reasonable. So any real gas is going to behave as a perfect gas in the limit that the pressure goes to zero. That is, the molar volume goes off towards infinity. Again, we've just seen for N2, the mean free path is 96 nanometers, whereas the diameter of my molecules is about 0.37 nanometers. The molecules are so far apart from one another, they never encounter one another. After a while, when you start to compress your system, so if we move from the right towards the left in this graph, we make the volume smaller, the molar volume decreases, and correspondingly the pressure starts to increase as it has to. But then it starts to drop off below what you would predict for an ideal gas. That is, the molar volume, the pressure is a little less than you would expect based on the molar volume. And it's less because the attractive forces start to become important. You've compressed things to a regime where the mean free path now is a few molecular diameters, right? And so the attractive forces between the molecules pull them together, which makes the gas a little bit more compressible. The pressure doesn't go up as quickly as you compress it as you would expect if it wasn't for those attractive forces, which is assumed in the ideal gas behavior. So the real gas becomes slightly more compressible than an ideal gas. Once you really compress things down to really small molar volumes, all the way down here on the graph, you can see that the pressure starts to shoot up, and it's there subtly, but you can't, it's maybe not completely obvious, but the red line goes above the black line at very low pressure. Okay? At that point, you've compressed the gas so much that the molecules are effectively in contact. The mean free path, if it's even a meaningful thing to think about anymore, is so small the molecules are touching one another constantly. And because they're touching one another, if you continue to press on them, they start to repel each other. So the repulsive part of the intermolecular potential, the fact that the molecules want to push each other apart because you push them too close starts to become important, and it becomes harder to compress them than you would predict for an ideal gas, where that approximation doesn't count. There are no intermolecular forces. So the pressure goes up more quickly than you would expect as you continue to compress. So the intermolecular forces operate differently in these two different regimes. Perfect gas at very low pressure, when the molecules are far apart, you decrease the average distance so they're a little bit closer. Gases become more compressible because the molecules attract one another. Compress it further beyond that, the pressure goes up more quickly than you would expect because the molecules are repelling one another. Yeah?
So, under high pressure situations, we can assume that the molar volume needs to approach zero. We also say that the mean free path just becomes insignificant at that point.
The mean free path, once you've compressed everything so much that the molecules are basically in contact, you don't really have a gas anymore, right? It's kind of a liquid or a supercritical fluid, as we'll see. But at that point, there is no mean free path as a meaningful concept because the molecules are in contact. So the mean free path has to basically be zero at that point. It works for gases. Once you get to these regimes where it's hard to define it properly as a gas, it's a little bit tricky. And on this plot here, I should say like moderate pressure is probably what I would consider to be fairly high pressure. I mean, we're getting to things where we're at 100 atmospheres, so 100 atmospheres of pressure, so 100 times ambient pressure is pretty high. Okay, so we can look at these isotherms for an actual gas and see what behavior we can expect for a real gas. Okay, so here's some isotherms for CO2 plotted in this picture here. And this one is missing its x-axis, so let me just quickly add some numbers. This is molar volume along the bottom, again, in units of liters cubed. Liters, per mole. So 0.2, 0.4, 0.6. So we can imagine we've got a cylinder, once again, equipped with a piston of some sort. My CO2 is in here. We're going to just decrease the volume to compress the gas within this piston. So the pressure for an ideal gas is RT divided by the molar volume. So what this graph is showing us is our isotherms, that is pressure against volume, at a constant temperature. And so every temperature you get a different isotherm. The pressure volume plot looks a little bit different. So let's consider what happens as we take our gas contained within the cylinder and begin to decrease the volume. And as we decrease the molar volume, as you would expect, the pressure is going to go up, right? You're compressing the gas, the pressure increases. So let's start off by thinking about what happens as the gas compresses at a temperature of 20 degrees C. So that is shown by this red curve here, which I can kind of highlight a little more. So under the label on it, you can probably see. So initially we have ideal gas behavior, right? You go from a large molar volume and we start to compress. The gas behaves ideally. Then it's going to reach some point where the pressure starts to increase. As we push the piston down, we find more and more pressure. Then all of a sudden, at this particular temperature, what's going to happen is all of a sudden the pressure will no longer go up as you continue to push on the piston, right? And that's going to happen because some of the gas will have formed a liquid, right? So the gas is going to liquefy. So at this point here, at 20 degrees C, the pressure remains constant. So even as I continue to push on my piston, the pressure doesn't change. But what happens within the container is that I have some gaseous CO2, but I also have some liquid CO2 that's present. And so what we have at that point, at 20 degrees C, the pressure is going to increase. Oops. Until a liquid forms. At that point, we have an equilibrium established between our liquid and our gas. And that happens at constant pressure, right? And the constant pressure is called the vapor pressure, which for CO2 at 20 degrees C looks like it's about 60 atmospheres, okay? So if you compress the gas, eventually you form a liquid. So you'll form two distinct phases present in this cylinder. There will be a layer of liquid at the bottom, there will be the gas above. The pressure of the gas will be 60 atmospheres. Push down on the cylinder a little bit more, the pressure remains 60 atmospheres, it doesn't change. What changes is you form a little bit more liquid. So you're liquefying the gas by continuing to decrease the molar volume, right? And that's going to continue to happen as you push down on the piston, as you continue to decrease the molar volume, until all of the gas has been converted into the liquid. At which point you have a layer of liquid with the piston resting directly on top of it. And if you continue to press, well, what you're doing at that point is you're just pressing on the liquid, right? And the pressure then shoots up dramatically because you've got molecules in contact and those repulsive intermolecular forces start to dominate and start to push things apart again. So you have to overcome that and continue to force the molecules closer and closer together. And so everywhere along this line, I have a liquid plus gas equilibrium. If I do the same thing at a lower temperature, well, if I encounter this shaded area on the graph at some lower temperature, well, that's, say down here, then I have an even longer line. Again, I have a different vapor pressure because I'm at a lower temperature, but I still have a liquid forms first, and then I've got an equilibrium between the liquid and the gas, so the pressure remains constant as you continue to decrease the molar volume, right? But you have a liquid gas equilibrium, but at a lower pressure. So that line is drawn at a pressure of, what would that be? That's about 30 or so atmospheres. So lower temperature, the vapor pressure of the liquid is smaller than it is at higher temperatures. I get a longer line on this particular graph. If I go to a slightly higher temperature, the line gets shorter. and the vapor pressure is higher, I reach a certain point in the graph, which is equal to this temperature of 31.4 degrees C, or 31 degrees C, we'll call it. For approximation, no liquid forms, right? I've reached, instead, an inflection point on the curve, right? So the pressure continues to go up, then it stays flat instantaneously as I decrease the molar volume, and then the pressure shoots up again. So that particular temperature, 31 degrees C, is known as the critical temperature. And at the critical temperature, you don't form a liquid, right? What happens is you continue to compress, you get a denser and denser and denser gas as you continue to decrease the molar volume, and then the pressure just continues to rise, but you never form a separate liquid phase that is distinct from the gas. It just coalesces into what's called a supercritical fluid. So at temperatures above the critical temperature, you can't liquefy the gas by compressing it, right? You just form this supercritical fluid. So at temperatures below, we form a liquid on compression. That is, we form distinct phases. A distinct liquid and a distinct gas phase. They're separate. There's an interface that's clearly discernible between the two. Exactly at the critical temperature, my isotherm merges to a critical point. We don't have this region of flatness where we can continue to compress and have this gas liquefaction process. It all just coalesces into a single point. And it's basically where these lines that you can draw across the diagram get shorter and shorter and shorter, so eventually the line drops to zero, right, as you increase the temperature. Above the critical point, you don't get this separation into two separate phases. Instead, what you get is a supercritical fluid. So there's no separation. You just get what is effectively a very dense gas. That's one way to think about it. The critical point, or the critical temperature, defines a critical point, which happens at a very specific molar volume and a very specific pressure. Okay, we're talking about this inflection point on the curve here. It's known as the critical point. Just mention this point. This critical temperature is important because it separates these distinct regions of behavior, and the pressure and the molar volume at the critical temperature at this inflection point on the isotherm defines my critical pressure and my critical molar volume. So this basically is the location inflection point on the isotherm. So you only get that inflection point at the critical temperature. So collectively, TC, PC, and VC are going to be called the critical constants of the gas. So we can form a liquid by compression only at temperatures less than the critical temperature. And the critical temperature is gas specific. So the table here shows some critical constant for a collection of gases. You can see the row there with CO2. The critical pressure is 72.9 atmospheres. The critical volume here is expressed in centimeters cubed per mole is about 94 centimeters cubed per mole, and this critical temperature is about 304 Kelvin. So that's the example of where those were on that previous picture. Other gases have very different critical temperatures. Oxygen, for example, its critical temperature is about 155 Kelvin. That is, if you compress oxygen, it won't liquefy unless the temperature is below 155 Kelvin. You can't liquefy oxygen. Other gases that you're probably familiar with can be readily compressed. A good example would be something like propane, which is going to be used to power grills and so on. You buy your little cylinder of propane, you can slosh it around, you'll hear a liquid. So the reason you can compress propane is that the critical temperature for propane is about 370 Kelvin, or 97 degrees C. That is if you're at a temperature below 97 degrees C and you compress propane, you'll compress it until it forms a liquid, and that means it will have a fixed vapor pressure at that particular temperature that your cylinder is at as well. So the pressure in the cylinder doesn't get any higher, it sits at the vapor pressure depending on the temperature, and most of the substance will be liquid until most of it's consumed. The other property in this table is called the compression factor, which I'm going to talk about next. I think I probably have time to quickly mention compression factors. Okay, let's wrap up by talking about how gases deviate from perfect gas behavior. Well, one way to define this is in terms of what's known as the compression factor. We're going to call this thing Z, and we'll just say it's the ratio of the molar volume divided of the actual gas, the real gas, divided by the molar volume of a perfect gas. So top is for real, bottom here is for a perfect gas. So for perfect gas, molar volume, give a little circle here to say identify this as the perfect one. We've already seen is the gas constant times the temperature divided by the pressure, all of which implies that for a real gas we can relate the I'll just say it's PBM 0 equals RT, and for a real gas we're going to write this P times its molar volume will be RT times Z, as is shown over on the left hand side. So the compression factor depends on the gas, and it depends on the pressure of the system. It tells you how much the particular gas deviates from ideal behavior, and different gases have different intermolecular interactions, so they deviate in different ways. The first thing to note is that at low pressure, that is, as the pressure goes all the way out to 0, then Z is going to converge on 1, and that's what this graph is showing here. Okay, the compression factor is being plotted as a function of pressure. Low pressure is all the way off towards the left on this graph. All of these different lines for the different gases effectively reach 1 at the low pressure limit. Right? That is, at the very limit of low pressure, all gases behave as perfect gases. So we're close up with this low pressure limit. You can see all of these lines eventually converge on 1, which go to 0 pressure. So all gases are perfectly. In between, at intermediate pressure, you have attractive forces that dominate, and you can see that for most of the gases that are shown in this picture, Z drops below the line that's equal to 1, right, which is at this point here. So Z becomes less than 1. And that tells us when attractive forces dominate. Or an equivalent way of saying that, when these things dominate, we're saying that the molar volume of the real gas is less than the molar volume of ideal gas. Increase the pressure and head towards the right. Well, you can see out there, the compression factor increases. It is now higher than 1 everywhere, and that's going to correspond to the situation